This question asks, find the equivalent capacitance for the drawing, given that C1 equals 3 microfarads, 6 microfarads, and 2 microfarads respectively, C2 and C3, and determine the total charge stored and the charge on C3 if 48 volts is the potential difference applied from point A to point B. Well, immediately we should see it says cross from A to B, so from here from here to here, it's 48 volts, which means that you can essentially assume a 48 volt battery is up here chilling, and it's putting in 48 volts. Which, if you think about it, if you watched the last video as well, this means that this whole area is getting hit by 48 volts. That means that C1 and C2, by the way, because they're going to work together, have to beat out 48 volts. C1, C2 over here as well have to beat out 48 volts, but C3 by himself is alone to beat out 48 volts, which means that it's asking for the total charge. No, the charge on C3 is the second part, and we can solve that immediately. We can go Q equals CV, or Q is equal to C3 times that 48 voltage that's coming right here. And we know that C3 is given. It says C3 is equal to 2 times 10 to the negative 6 farads. So C3's charge is going to be equal to 2 times 10 to the negative 6 times 48. And you're going to get 9.6 times 10 to the negative 5th coulombs. And that's the answer immediately. That's the charge on C3. But the other question, turn the total charge stored in the entire thing, is much more annoying. But it's nothing more than much more annoying, I promise. But we have to follow these rules. So capacitors in series are like resistances in parallel. So we have to go C1 times C2 over C1 plus C2. The good news is that this is the same as that one, so we don't have to do this once. And you're going to get that those are equal to 2 times 10 to the negative 6 farads as well. But now, so these can be crossed out for a single capacitor that's 2 times 10 to the negative 6, as well as a single capacitor on this side that's 2 times 10 to the negative 6. You just get rid of these. So now they've been replaced. But that means you have a 2 times 10 to the negative 6 farad capacitor, a 2 times 10 to the negative 6 farad capacitor, and another 2 times 10 to the negative 6 farad capacitor. And they're in parallel. Capacitors in parallel add. So you're going to have 6 times 10 to the negative 6 farads. So now this whole thing can be replaced by a single capacitor that's 6 times 10 to the negative 6 farads. But we're not quite done. We still have to deal with this bottom part that's hanging off. And they're in parallel, so treat them like they're in series. C2 plus C2. C2 plus C2 is equal to, it's just going to be equal to 12 times 10 to the negative 6 farads. C2 plus C2. Yep. Then, so now it's simplified to a point where if we have A, we're going to have a capacitor of 6 times 10 to the negative 6 for the top part. And now we've simplified to a point where these were combined into that single 12 times 10 to the negative 6 farads capacitor. And once again, now they're in series. So now we have to treat them like we would a resistor in parallel. So we're going to have to, they're just opposites. Think resistors, but flip your logic, and that'll be correct. It's 10 to the negative 6 farads. Oh God. Whatever. 6 times 10 to the negative 6 farads plus 12 times 10 to the negative 6 farads. And that is going to be your final total capacitance. So, of the entire thing. So 6 times 10 to the negative 6, so times 12 times 10 to the negative 6, divided by 18 times 10 to the negative 6. And you're going to get 4 times 10 to the negative 6 farads. And that's it. That's the total capacitance. Now again, it's asking for the total charge stored, not the total equivalent capacitance. And that's just going to be this equation right here. So we're going to say, okay, now we're looking at the total. So Q is equal to 4 times 10 to the negative 6 that we just found, times the total voltage going in, which is 40 volts. And that's going to give you 4 times 10 to the negative 6 times 48. You're going to get 1.92 times 10 to the negative 4th coulombs. Whatever, I'm going to put it down there. And that's going to be your final answer for the entire system's charge that it can store. And that is it. Like the big thing here is that, I mean, like they're essentially, when you're doing this type of math, they're resistors. Just treat the logic like they're resistors, but flip it. So when they're in series, treat them like they're parallel resistors, and when they're parallel, treat them like they're series resistors. It's just flip the logic. That's all there is to it. That's the only trick. And remember this equation. This Q equals CB. Nice and easy. And that's it.